Morning. Today I wanted to go over what I wanted to accomplish to run a set of LED strips. I got these strips, actually a series of strips from a scrapped LED TV a while back, and I've been sitting on them for some time now and decided to fix them up and hopefully put them to some use. The problem with LED strips though is that the LEDs are almost always going to be in series, so there's going to be a high forward voltage to overcome to light them. So in this particular strip we have 5 LEDs, and at something over 3 volts, we're going to have ideally maybe 15 or 16 volts to overcome, at least to light them, and then whatever voltage to pass enough current to them. So there are LED chip drivers that would be optimal to use, but I don't have any that would provide a boost voltage to meet the forward voltage required to run the strip. So for that task, I'm going to use the vulnerable MC34063 buck boost inverter chip. Although it's not really the modern ideal chip for any of these tasks, it should be able to perform the task to boost the voltage just fine. So first things first, we kind of need to see what voltage we're going to want to run the strip at. All right, so I have my power supply set up here, and I'm just going to light the strip. And I know that these should be around 3 volt LEDs, and they should consume their max about 20 milliamps. So I have the power supply set to just 1.6 volts at the moment. And we're going to ramp that up and see kind of how much power they draw and how much voltage they take. So let's see, probably should be around, okay, they light at 13. I don't know if you can see that on the camera. So let's just keep going. So around 15, they're all obviously lit. Let me maybe turn the lights out here. Yeah, that's better. But they're only drawing 9 milliamps. At 20 apiece, we should be drawing 100 max. So it seems as though the voltage is going to be much higher than 3 volts a cell. And really, I got these from eBay, and I don't know if the data on them is correct, but I have many of them, so if we kill one, we'll be able to replace it. So I may run them a bit higher. I'm kind of liking around 20 volts. It's not the full 100 milliamps, and it's not going to get hot at this voltage and current either. So we may want to set the voltage in our boost converter to around 20 volts. All right, so we're going to aim for about 20 volts, and I have a boost converter board that I built a while back here. So I'm going to calculate some values for the components and assemble the board and test it out.
Okay, so we need to calculate some values for the MC34063. So first thing we're going to do is to just Google the chip. Let's go find the data sheet, and we can scroll down to the values here. Where are they going to be? Okay, so this is the first place you'd probably think to go to calculate the values for the chip for like the timing capacitor, how fast you want the chip to run from 0 to 100 kilohertz. See how much out of 1.5 switching frequency max current. You calculate how much that's going to be the sense resistor here, the inductor here and the output capacitor. So you could go through all this, do all the math, but you're going to calculate values that you're probably not going to have exactly. So I find it kind of useful sometimes to use a calculator, and there's a good online calculator. Nomad.ee. So this allows you to calculate some values kind of on the fly. So you don't spend 5-10 minutes doing the math to calculate your values and realize, I don't have, a 213 picofarad capacitor. I have a 230. How is that going to affect things and so forth. So I'm going to plug in the values here that I would like to use. I think we're drawing 100 milliamps. So, or max, that's kind of what we want, but it's more like 80. Ripple, it doesn't really matter that much. And then for smallest inductor size, I want to run the fastest possible frequency. So we can see 173 picofarad cap. The peak switch current is going to be 350 milliamps. Sense resistor, they want it to be 0.85. Wow, the inductor 135 microhenries. I don't have anything like that probably. Only a 40 microfarad capacitor. We could obviously go larger. This resistance value here, I think that's usually just 180 ohms I've seen. I'm not sure. And then the feedback divider down here, they've set these values, which is nice. So 1K and 15K for us. So that's pretty nice. So that's one way to do it. You can always mess with the output. So let's just say we want to draw 500 milliamps. It's probably going to be higher switching current than I can produce. Yeah, it's going to give me a warning here. So let's just go down 400. So now we're down to a 0.2 sense resistor. We're up near the max switching current. And our inductor size has fallen significantly. So kind of more to the level of what I'll have. And with this chip, I've kind of noticed that the higher the inductor value, kind of the better outcome you're going to have, especially if you're drawing more current. So the fact that it shrinks the inductor when you're trying to output more current I've kind of noticed that's not necessarily what you want. And everything else is basically the same. So I'll see, I probably have something like this, okay? But then another final calculator that I really like is something I found at a site called the ETG, and this is a calculator for the MC34063 on the spreadsheet, which is actually very useful as well. In fact, this is probably my favorite calculator for this. Although I downloaded this from their site, I watched, they have a video up, maybe I'll post it. There were some incorrect values, I can't remember where anymore, it's been years. But I've corrected them in this spreadsheet, but they had some of the formulas just slightly incorrect. So that's something to watch out for. I'll have to see if I can figure out what those were. But this is very helpful. You can plug in all kinds of values here too. Oops, what am I doing? Okay. Let's plug in 20. So then we get the same values here that we'd be getting over there. 33 mic. So these could all be changed. You could change the multipliers here. get a little bit more readable values. So anyways, this is pretty useful. So there's kind of the three methods. You calculate it on your own. You can use the online calculator, or you can use a spreadsheet calculator like this, which is probably my favorite method. So I'm going to take note of the values that I need, and I'm going to build up a board, and let's see how it works.
Alright, so the board is constructed. I guess we have yet to place the chip. Let's do that. According to the board layout, it faces this way. Hope that's right. Oh boy, look at that. Our legs poking up. That's wonderful. Got crunched. Alright, looks like we got it this time here. Unfortunately, this board I did not mark the polarity of the plugs, either of them. If there's ever another revision that is going to be done, that will need to be changed. So let's hook up some wires and let's see if we get 20 volts on the output. This can also fit a barrel jack, but in this case I don't want a barrel jack. So this other foot crank fit pretty nicely right over the top. Okay. I'm fairly sure I have the polarity correct. Let's feed this, feed this 12 volts. Oops. A little bit much, well, it's fine. Okay, and let's do a meter let's do a little bit of current limiting here because I don't want to blow this thing up if something's wrong with it right away. Just have to take my word that I'm watching the power supply, and looks good. Use a bunch of current right away because there's no soft start on these. All right, so it's powered up, and got the little LED on here as well. And I believe that's positive, and that is negative. And look at that, 19.7, no load. So that looked pretty good. Should we hook up the strips? Let's hook up the strips. Let's cut the power briefly. So I was correct. Put my polarity here. I'm gonna screw this. But these jacks are not the greatest screw terminals, but they're okay. Okay. And let's focus on the power supply and the strips. Let's give it power. Oh, that's a bit of current, but of course, they're not going to be 100% efficient, of course, like before. So let's just see what the voltage is, because that's kind of my main concern. We're still at 19.7. Get the polarity wrong there again. 19.7 volts. So that's it's probably getting as much current as I want it to. So looks like the power supply for these is all well. We can power this via a 12 volt barrel jack. The reason I didn't want to go with the barrel jack though is because I still need a switch. I don't want to have to unplug this from the wall. And what I was thinking would be neat would be, let me grab my other lights here. So these, I already have these, I have pointing towards the floor. I have a bunch of boxes of parts and stuff down there. And these have a nice on-off touch sensor. So I'm thinking I'd like to do something like this because it's going to be under the table. So it's kind of sitting like this, and I need to see my parts boxes or my toolbox or something. I just turn it on, and I think I'm going to mount these under my other table. So actually too, I've also bodged in a barrel jack on this guy. So we're going to look into a switch for this, a touch sensor switch, so I can just easily turn them on and off under the table like that. So I noticed the circuit with the 555 timer. Alright, this is a touch switch I built using the 555 timer. I'll just go over the basics. It's extremely simple circuit, as you can see. We have two resistors. We have N-channel MOSFET here. We have a bunch of terminals. That's about it. So we have the output, pin 3, going high and low. We have a pull-up from VCC to pin 2. This is a touch sensor. This is a touch sensor. Off, on. So we have a low rail and a very weak pull-up, 10 mega ohm pull-up to pin 2. And on the bottom we have pull down to pin 6 and a VCC high rail right here. So that'll flip-flop the output here. And so we have the output with the input power. And this is good up to 18 volts. So what I'm going to do is to run 12 volts, and then we'll be switching the power for the supply. So as the switch is high enough. So I built this up. This is what I've come up with here. Very simple. I actually included an LED here, just as extra. If there's no low, we can see if it's working or not. So we have touch, output, input. So let's hook this up and give this a try as well. Alright, I think we have everything basically in one shot. I have 12 volts coming in from just an adapter. We have the touch switch right here, which basically just it's just an extra PCB I had, and I just ran some bare copper wires, which probably should be tinned. They're going to corrode. I don't know how well they're going to work if they corrode, but I'm planning on mounting that, and then I'll just have to mount the rest of the stuff under the table as well. Just the 555 timer and the boost converter here. Alright, so these 10 mega ohm pull-ups could be modified depending on if the circuit, if they're too weak or strong potentially even. So right now it's working. I can touch here and touch here, and they turn on and off. But depending on maybe the moisture of your finger or something like that, things could, be different. So these are working fine for me right now. So I will just go ahead with this, mount this up, and it looks good to go. Shorten some wires, figure out how I'm gonna mount this stuff. So another thing to note is I actually used a 100 microhenry inductor here. Pretty nice one. I actually salvaged this one from something else too. So it's probably a little bit overkill, probably a little bit too nice of an inductor for this board, but usually going with a little bit higher value really can't steer you wrong, at least in my practice that I found with this chip. So and also this isn't able to source too much current, obviously. So if we're going to be lighting longer strips and stuff, actually that's something else to know. This strip, I was replacing some of the LEDs on it, and I couldn't get one off. I don't know if it didn't get hot enough, the strip didn't get hot enough or something, but I actually had to cut this strip, the bad LED, out, so I was left with 5, and then here's the 6th one, the starting one, and I cut the bad one out. So in running more LEDs in series as I would in a longer strip, and also these are very low power LEDs. These are 20 milliamp LEDs, whereas the other strips, I have 3 of them. I ran these 150 milliamps per LED, something like 3.5, 3.3, 3.4 volts. I mean, these strips will consume much more current. I think something like this will just about run them, but if I wanted to run more, a couple strips maybe even, you can modify the schematic a bit of the chip and use an external switch right here, NPN transistor. So I built up one of these, just testing some stuff out. The efficiency's a little bit worse off actually, just in testing. Usually getting about 80% efficiency, 80 something around that on these guys with the built-in switch, and on this usually about 73, 72, something like that. So may depend on the transistor. I'm using the tip 41C on this guy. I've tried the tip 120, the Darlington pair transistor. It didn't seem to work out too well. This transistor seems to work. I used a monster inductor, 220. I can output about an amp from this from 12 to 24 volts. I can output an amp, and this will get quite hot under that. This heatsink is far too small for that. But I used a 0.1 ohm resistor. I have a trim pot on here, so I can adjust anywhere from about 15 volts to 28 or something like that. So pretty much it's similar to the other design. using a 220 puff, timing cap, adjustable feedback. I think I have a 1K into a 1K pot, and then a 22K divider, and of course the 220 microhenry inductor and a 0.1. I think I'm using a 180 here too. That's just to bias these transistors. I'm actually not using this pull down on the base of this tip 41C. I actually didn't notice any difference in efficiency or performance without it. I can easily add it in, but I'm not sure about that. So, and I'm using a 2 amp diode just for safety there too, and I think a 330 out, microfarad out, put capacitor. It's actually a 470 in, 330 out. So there's always that option. Performance is a little bit less, but you can get more current from it. You need good heat sinking, of course, though, the more power you go. So thanks for watching.